So let's talk about some applications of integration. In this video, I'd like to introduce the idea of using integration to find the area either under a curve or between two curves. So let's focus on this first graph I have here where we can see that we have two bounding curves for a desired region. One of those is f of x and one of those is g of x. And what I'd like to do is first think about the area between these two functions using what I'll call vertical slices. And that's exactly as it sounds. What I can do here is think about taking my region from A to B along the x-axis and breaking that up into n pieces of equal width. Just like we've seen with Riemann sums before, I take the length of that interval and divide by the desired number of rectangles. And we can define the edges of those rectangles along the x-axis with our same xk formula. So all of this is exactly what we've seen with setting up an integral before. But now in thinking about the area between two curves rather than just simply underneath one, if I were to start to sketch out these slices, let's focus on, let's call it the kth rectangle. So I have xk minus 1 and xk. Then you can see that the edges would intersect then with the curves here. And as we've seen with Riemann sums, there are lots of different choices we could make for the height of my rectangle there. For the purposes of this video, let's just sketch out, say, a left hand. But so if I did that, then what's going to happen is there are really going to be two places where I use a left value. So I can really get rid of this kind of bottom part here, and this rectangle would approximate the area under, or not, I shouldn't say under, the area between f of x and g of x in our kth subinterval. So in terms of doing that, you can imagine I could take this region, break it up into several rectangles, and as we've seen with Riemann sums before, then I would want to add up the area of each of those rectangles. Now, to think of the area of this rectangle, well, the width is still delta x, but let's think about what the height would be. One way to gauge this distance is you can imagine that the distance from here down to here, that distance is f of xk minus 1. And the distance from here to here is, of course, g of xk minus 1. And consequently, the difference of those two, notice, would give me the height, right? I can subtract the red line from the blue line. So that difference is f of xk minus 1 minus g of xk minus 1. And as I said before, we multiply that height by the width delta x. Now we would do this for all of our k values, add that up, and we're going to end up with the area then is approximately the sum from 1 to n, so n being our number of rectangles, of the area of those rectangles. So f of xk minus 1 minus g of xk minus 1 delta x. And as we've seen before, now I can think about taking the number of rectangles n, sending that to infinity, and from this I can see that that Riemann sum, if I let n go to infinity, then I should get the exact area. And what's going to happen here, and like I said, I just arbitrarily did a left-hand sum before, but for any of these Riemann sums, this will become the integral. The delta x is now going to be dx. The height is, we don't want to have our dependence on k anymore in this integral, f of x minus g of x. And we want to be careful, remember the bounds on the integral have nothing to do with the bounds on the sigma notation. Instead, we know that our x values range from a to b from our given picture. So those would represent the bounds on the integral. So we get this formula here. One thing I do want to emphasize is in terms of the role that f and g are playing, what's significant here is that in this picture, f is above g of x. And so consequently, that's why I have f minus g. If the picture were different so that you had g was above f, then you would have g minus f. And beyond that, you can imagine that maybe you have two curves where the role of the function that is higher up changes, but we could always split that up. So if I had, this is, let's pick a different color maybe. Suppose this is f of x and this is g of x. Well, you could split that into two curves here. And the significance would be that to the left of my vertical line, you would be able to integrate f minus g. And to the right of my vertical line, you could integrate g minus f. So you always want to pay attention with these vertical slices, which graph is vertically higher up than the other in terms of setting that up. Now, the other thing I want to emphasize, though, is that you don't have to slice vertically. We might choose to slice horizontally. In this picture, we really get kind of an equal amount of effort to do so. But it might be easier, depending on what the functions are, to look at the vertical slices. So I have the same graph here, but let me think about instead, if I were to slice this vertically, what I would want to think of here is, first of all, to focus on the interval of y values. So I've marked that C to D. So, whoops, let me go back to the. So if we have not vertical, but horizontal slices, then I'm going to take my interval of y values and chop that up into n equal pieces. So I take the length of that interval divided by n, and I'm going to define my y sub k as the smallest y value, c, plus k times that change in y. So this is the same idea that we've seen with Riemann sums, but now I'm focusing on the y-axis. So I can once again kind of envision a subinterval within here, the kth one. So let's look at edges y sub k minus 1 and y sub k. And we could look at a picture and think about the rectangle that we would get out of this. So again, I could choose lots of different ways of constructing this to get a rectangle. One way we could do that is to focus on the value of the function, let's say at y sub k. So in this instance, I might look here. And so we would look at our rectangle as being this one. Again, I can kind of get rid of part of this. And so this is one way to kind of estimate the area of between the two curves, at least for that little subinterval. Now, notice that, again, what I can do is start to think about how I would find then the area of this rectangle. And we've already computed here this notion of delta y. That's going to be our width. And one thing we have to consider here is how are we going to find the appropriate values to mark off here? Well, we can think about expressing this not as a function of x, but instead as a function of y. And in doing that, what we're really interested in is, of course, what are the values along here, because we want to measure those distances. And notice that to get, let's see my colors, to get, first of all, this length, that is actually going to be f inverse of y sub k. We want to know the x value that's coming in there. And to get this distance, likewise, we can find g inverse of y sub k. So, of course, there are some underlying assumptions here that it is possible for us to actually find that inverse. But given that, then we can see that the length, or, depending on which way you want it, one dimension of this rectangle is going to be the length of that blue part minus the red. So I can express that as F inverse y sub k minus G inverse y sub k. And the other dimension is what we're calling delta y. Notice that, again, arbitrarily, I plugged in y sub k instead of y sub k minus 1. So in comparison to my vertical slicing above, I just made a different choice in terms of my scheme. It doesn't matter. I'm just talking about roughly approximating this. But when we send the number of rectangles to infinity, it wouldn't matter which choice I had made there. So what we get here is that the area of the entire region is roughly equal to the sum of the area of all of my n rectangles. And again, I'm going to use my formula that I've looked at above to get F inverse of y sub k minus G inverse of y sub k times delta y. To find the exact area, we would send the number of rectangles, n, to infinity. This would give me an integral. And importantly, now it's an integral with respect to y. And we see that the integrand is F inverse of y minus G inverse of y. And again, the bounds on my integral come from the knowledge of my interval on the y-axis, which we see ranges from, in this picture, C to D. And just like I said before, it does matter here which function is further away from the y-axis. And in this picture, that was the function f, and that's why I did f inverse minus g inverse. So you can always look at your picture and gauge kind of which role each function is playing when you have bounding functions for a desired region.